One of the hardest things when working with database transaction is locking and handling deadlock. From my experience, the best way to deal with deadlock is to avoid it. By that I mean we should fine-tune our queries in the transaction so that deadlock won't have a chance to occur, or at least minimize its chance of occurrence. And that's exactly what I'm going to show you in this video. Alright, let's dive in. This is a money transfer transaction code that we've implemented in the previous lecture. Basically, we have fixed the deadlock issue caused by the foreign key constraint. However, if we look at the code carefully, we can see a potential deadlock scenario. Here in this part of the transaction, we're updating the balance of the from account and the to account, and we know that they both require an exclusive row level lock to perform the operation. So if there are two concurrent transactions involving the same pair of accounts, there might be a potential deadlock. But we already have a test that runs 5 concurrent transfer transactions with the same pair of accounts, but deadlock doesn't occur, right? That's correct. However, the transactions in our existing test all do the same thing, transfer money from account 1 to account 2. What if some of them transfer money from account 2 to account 1? To illustrate how deadlock might occur in this scenario, I have prepared 2 transactions in Table Plus. The first transaction will transfer $10 from account 1 to account 2 by first subtracting 10 from the balance of account 1 and then adding 10 to the balance of account 2. The second transaction will do the reverse work, transfer $10 from account 2 to account 1. First it subtracts 10 from the balance of account 2. Then it adds 10 to the balance of account 1. Now let's open the terminal to run these 2 transactions in 2 parallel PSQL console. First I will start the first PSQL console and begin the first transaction. I'm gonna run its first query to subtract 10 from account 1's balance. As you can see, the account is updated instantly. Okay, now let's open another tab, start a new PSQL console, and begin the second transaction. Now let's run its first query to subtract 10 from account 2's balance. This query also returns immediately. Now back to the first transaction and run its second query to update account 2's balance. This time the query is blocked because the second transaction is also updating this same account. If we go back to Table Plus and run this query to list all the logs, we can see that this update account 2 query of transaction 1 is trying to acquire a share lock on transaction ID 911, but it is not granted yet because transaction 2 is already holding an exclusive lock on the same transaction ID. Therefore, transaction 1 must wait for transaction 2 to finish before continue. Now if we continue running the second query of transaction 2 to update account 1's balance, we'll get a deadlock because this account 1 is being updated by transaction 1. Thus transaction 2 also needs to wait for transaction 1 to finish before getting the result of this query. Deadlock occurs because these 2 concurrent transactions both need to wait for the other. Okay, now let's roll back these 2 transactions. Then go back to our Simple Bank project to replicate this scenario in a test. It's going to be very similar to the test that we've written in the last lecture. So I will just duplicate this test transfer tx function. Change its name to test transfer tx deadlock. Then here, let's say we're going to run 10 concurrent transactions. The idea is to have 5 transactions that send money from account 1 to account 2, and another 5 transactions that send money in the reverse direction from account 2 to account 1. In this scenario, we only need to check for deadlock error. We don't need to care about the result because it has already been checked in the other test. So we'll remove this result channel. Now inside this for loop, let's define 2 new variables. From account ID will be account1.id and to account ID will be account2.id. But since we want half of the transactions to send money from account 2 to account 1, I will check if the counter I is an odd number or I modulo 2 equals to 1. Then from account ID should be account2.id and to account ID should be account1.id instead. Alright, now inside the Go routine, we should change this field to From Account ID and this field to ToAccount ID. Then remove this statement because we don't care about the result anymore. This result variable is no longer needed, so let's replace it with a blank identifier. Okay, now the check errors part. Let's delete this existed map and everything inside the for loop except the error checking statement. We also want to check the final updated balance of the ToAccount. In this case, there are 10 transactions that move the same amount of money between account 1 and account 2. But because of this condition, 5 of them will move money from account 1 to account 2, and the other 5 will move money from account 2 back to account 1. Therefore, we expect that in the end, the balance of both account 1 and account 2 should be the same as they were before the transactions. So here, updated account 1.balance should equal to account 1.balance. And similar for account 2. Okay, let's run this test. We've got a deadlock error as expected. Now let's learn how to fix it. As you have already seen in the example that we ran in PSQL console, the reason deadlock occurs is because of the different order in which two concurrent transactions update the account balance, where transaction 1 updates account 1 before account 2, while the other transaction updates account 2 before account 1. So this gives us an idea of how deadlock can be avoided by making both transactions update the account balance in the same order. Let's say in this transaction 2, we just move this update account 1 query up and keep everything else the same. So now both transaction 1 and transaction 2 will always update account 1 before account 2. Let's try to run them in the PSQL console to see what happens. First, begin transaction 1. Run its first query to update account 1. Then switch to the other console and begin transaction 2. Also run its first query to update account 1. Now, unlike before, this time the query is blocked right away because transaction 1 is already holding an exclusive lock to update the same account 1. So let's go back to transaction 1 and run its second query to update account 2. The result is returned immediately, and transaction 2 is still blocked. Now let's commit the transaction 1 to release the lock. Then go to transaction 2. We can see that it is unblocked instantly, and the balance has been updated to the new value. We can go ahead and run the second query to update account 2, then commit transaction 2. All successful and no deadlock occurs. Alright, so now we understand that the best defense against deadlocks is to avoid them by making sure that our application always acquires locks in a consistent order. For example, in our case, we can easily change our code so that it always updates the account with smaller ID first. So here we check if argument.fromAccountID is less than argument.toAccountID, then the fromAccount should be updated before the toAccount. Else, the toAccount should be updated before the fromAccount. Let's copy this block of code that updates toAccount and paste it here. Then copy this block of code that updates fromAccount and paste it below the previous one. Okay, now after this change, we expect that the deadlock should be gone. Let's rerun our test. It passed. In the logs, we can see the balances are the same before and after the transactions. Perfect. Before we finish, let's refactor the code a bit, because it now looks quite long and somewhat duplicated. To do this, I'm going to define a new add money function to add money to ToAccount. It will take several inputs: the context, the queries object, the ID of the first account, the amount of money that should be added to that first account, the ID of the second account, and the amount of money that should be added to that second account. This function will return 3 values: the first account object, and the second account object after updated, and a potential error. Inside this function, we first call queue.addAccountBalance to add amount 1 to account 1's balance. So the ID should be account ID 1, and amount should be amount 1. We set the result to the output account 1 and error variables. Then we check if error is not nil, simply return. Here, because we are using named return variables, so this return with no parameters is basically the same as if we write return account 1, account 2, error. This is a cool syntax feature of Go that makes the code more concise. Okay, next we do similar thing to add money to account 2. This ID should be account ID 2. This amount should be amount 2. And at the end, we just need to return without any parameters. Now with this add money function in hand, we can go up here to refactor our transfer transaction. If from account ID is less than to account ID, we want to update from account before to account. So here we call add money, pass in the context, the query, argument.fromAccountID, minus argument.amount because money is moving out, then argument.toAccountID, and finally argument.amount because money is moving in. The output of this function call should be assigned to result.fromAccount, result.toAccount, and error. Else, in case toAccountID is smaller, we want to make sure that toAccount is updated before fromAccount. So let's copy this command, but change this to result.toAccount and result.fromAccount. The first account ID that we pass in the add money function, in this case, should be argument.toAccount, and its amount should be argument.amount, since money is going in. Then the second account ID should be changed to argument.fromAccountID, and its corresponding amount must be minus argument.amount, since money is going out. And that's it. The refactoring is done. Let's rerun the test transfer tx deadlock. It passed. Excellent. Let's also run this normal test transfer tx. Also passed. And finally, we run the whole package test. All passed. So everything is now working properly. Deadlock is no longer a threat to our application. And that's the end of today's lecture. I hope it's useful for you. Thanks a lot for watching. Happy coding and see you in the next video.